Hello everyone, this is Professor Keene. We've been talking about Chapter 6 in A Student's Guide to the Great Physics text, where Galileo is discussing beam breaking. We've gone through the law of the lever, and then we went through two of his propositions, which talked about the tendency of beams to break and how it depends on the shape and size of the beam. So in particular, in Proposition 1, we discussed how a longer beam sticking out of a wall tends to break more easily when you apply a transverse force to it. In Proposition 2, we talked about how a beam, when it's sticking out of the wall, is going to it's going to be easier to break it in certain orientations than in other orientations. Notice that both of these propositions, Proposition 1 and Proposition 2, had to do with applying a transverse force to a beam. So let me make a sketch right here. So we've been talking about, oops, let me use a different color. If we had a beam sticking out of a wall, I'm just going to draw the part that's sticking out of a wall. And we've been talking about what happens when you apply a transverse force to the beam. This might be a case where you have a hook or something on the end, and as Galileo shows, you attach a string and then a bucket and you pour lead into it or some other heavy rocks to apply a transverse force. That's the kind of situation we've been dealing with so far. In the next two propositions, Proposition 3 and Proposition 4, we're going to be considering a different kind of force. Not a force where you apply a transverse force using an external weight, but rather a transverse force that is applied by the weight of the object itself, so the beam itself. So I should point that out right away, or highlight that right away. So in propositions 1 and 2, we ignored the weight of the beam. The weight of the beam itself, and concentrated on an externally applied, we might say, an externally applied transverse force. Realistically, the beam itself has weight, so even if you don't apply a transverse force, this beam will attempt to break under its own weight. That is what we're going to deal with in Propositions 3 and 4. So, in Propositions 3 and 4, Propositions 3, Roman numeral 3 and 4, we will consider how the weight of the beam itself, the weight of the projecting beam itself, it's projecting out of a wall, itself gives rise to a transverse force that works to break the beam under its own weight, so to speak. Okay, so that's just giving you a heads up of what we're doing. Realistically, in many cases, you'll have the weight of the beam itself trying to break it, and then perhaps a transverse force trying to break it as well. So those are going to be conspiring both to try to break the beam. And of course, there's the internal resistance force that's trying to hold it together, hold the beam cohering to the part of the beam that's inside of the wall. Okay, so let's talk about Proposition 3. I'll probably only get through Proposition 3 in this lecture and probably go on to the next proposition in the next lecture. So this is on page 79 in A Student's Guide. And the question that we're asking is, can an object, such as a beam, can an object like a beam break due to its own weight I hope you can read my writing, rather than by an applied force due to its own weight? And if so, how does the breaking moment I'll remind you what we mean by that in a moment. How does the braking moment increase with the thickness and the length of the beam? So we're assuming for the moment that we're not changing the material. We're keeping the material of the beam the same. If it's marble, let's say, we're going to keep it marble, but we're imagining making it longer and making it thicker. And how does that affect its tendency to break under its own weight? So let me draw a picture here. So here is a wall. Let's draw this beam sticking out of the wall, as we've been doing so far. Okay, and let me put some markings on here to indicate the length that is sticking out of the wall and the thickness of the beam. Again, we're going to assume that this is a square cross-sectional beam, so it's D high and D deep. Okay, and then as usual, we're going to consider this point down here to be the fulcrum about which it is trying to rotate due to the braking moment. And this resistance, the longitudinal resistance, is trying to support it with, once again, this lever arm right here. And then what is trying to break it? You know, before we had taken a transverse force and applied it to the end, but now we're going to consider the weight of the beam itself. Okay, now notice that the beam is extended out, so each little slice of the beam, if we think about the distances, various distances from the fulcrum, each slice has its own weight and is applying its own torque or moment trying to break the beam. So this little slice right here has its weight, and it is applying a downward force, a weight, that is the distance from here to here, so that's applying its moment. And then there's another little slice right here that's applying a downward weight, and another slice right here that's applying a downward weight, and so on, all the way to here. The ones that are farther out are applying a larger braking moment. The ones that are closer in are applying a smaller braking moment. But overall, we can simplify this situation by saying, let's just consider a point in the middle of the beam. We'll call this the center of gravity, and consider all of the weight as being concentrated here, and there's a single force acting down, which is kind of the sum of all these forces. And this is the weight of the beam here. Okay, so you can see that that's a certain distance from the fulcrum. This would be the distance from the fulcrum of that weight. So we can consider the braking moment to be equal to the weight of the beam itself times the lever arm, which in this case would be L/2. That is halfway down the beam. Okay? All right, so you might think right away, so this question is, how does the braking moment increase with the length of the beam? And you see right away the braking moment seems to increase linearly with the length of the beam. That is, if you make the beam twice as long, the braking moment will go up by a factor of 2. If you make the length 3 times as long, the braking moment will go up by a factor of 3. As you make it longer and longer, there will be a larger and larger braking moment because of the larger lever arm. That's what you would think at first, but that would be mistaken, because the weight also is dependent upon the length. As the length increases, the weight of the beam also increases because it has more volume and hence more mass, hence more weight. So there's secret factors of length in here, or rather non-explicit factors of length in here. They're hiding in the weight. So let's try to make explicit how the weight depends on the length, and then whatever factors of length show up here and this factor of length will both give rise to an increase in the braking moment. So what do we mean by the weight of the beam? Well, the weight of the beam is going to be related to its mass and also a conversion factor g that converts a mass into a weight. We'll come back and talk more about this when we get to Newton and Newton's laws of motion. But if you'll just suspend disbelief for a moment and allow us to talk about weight in pounds or newtons in terms of the mass of the beam and this conversion factor g, which is 9.8 meters per second squared if you would like to use the MKS system of units. Okay, so that's going to be the conversion between mass and weight, and then we've still got this L over 2. Again, if you're uncomfortable with this, if you can just suspend disbelief for a couple weeks, we'll come back and talk about the relationship between mass and force. Okay? Now, the mass, so g is the acceleration of gravity. That does not depend on the length of the beam, but the mass does depend on the length of the beam. How does the mass depend on the length of the beam? Well, the mass of the beam is just the density of the beam. I'm going to use the Greek letter rho for density times the volume of the beam. So I'm converting the mass into density. Let me go like this. Mass is going to be density times volume, and we've still got this g, and we've still got this L over 2. Okay? All right, and so now the density, of course, doesn't depend on the length. That's an intensive property. It depends only on the material. G, again, doesn't depend on the length, but the volume of the beam does depend on its length. Okay, so let's make explicit how the volume depends on the length. So we've still got this density. What is the volume of a beam? Well, if we assume that it is a rectangle or a square cross-sectional beam, then the volume should be its cross-sectional area times its length. So what is the cross-sectional area? It's just going to be the diameter of the beam squared times its length, times g times L over 2. So this right here is what we're replacing the volume by. And now we can see that if you keep the diameter the same and you just increase the length, we have shown how the weight of the beam depends on the length of the beam. So let's combine all these things together. I'm going to drop the parentheses and leave the density and the diameter squared and g, and I'll put the over 2 right here, and then we've got a length squared. Okay, so all this stuff does not depend on the length, but here we made explicit the dependence of the braking moment on the length of this beam. So you can see right away, what does this mean? This means that the braking moment scales as it's proportional to the square of the length. Okay, all this other stuff is going to stay constant, and as you increase the length, we see if you double the length of the beam, the braking moment goes up by a factor of 4, because 2 squared is 4. If you triple the length of the beam, 3 squared is 9, you'll increase the braking moment by a factor of 9. So there's not a linear dependence of the braking moment on the length. There's a power law dependence. It goes as the squared of the length. Okay? And you might think about this intuitively, what's happening. As you lengthen the beam, the lever arm is increasing linearly, and the weight is increasing linearly. And so there's two ways that the braking moment depends on the length. One shows up as a lever arm, and one shows up as an increasing weight, and that's why the braking moment goes as the length squared. And this is the point that Galileo is making in proposition 3. If you're interested in the tendency of a beam to brake under its own weight, then as you increase the length, the braking moment increases as the length squared. I'm going to stop there, and next time I'm going to talk about proposition 4, and I'll just give you a heads up of what proposition 4 says. It's, again, considering the weight of the beam, and what it is asking is, for a beam sticking out of a wall, how does its resistance to transverse fracture by a force increase with the length and the diameter? Oops. So I guess in proposition 4 I should mention that this doesn't deal with the weight of the beam. Proposition 4 deals with a transverse fracture.